All right, today's lesson is 16.5, Curl and Divergence. Two very, very cool concepts here for chapter 16. So what we're going to be able to do is we're going to be able to, it says define del. We've already defined del in the past. We're going to redefine del. We're going to define curl and define divergence. We're going to do a few examples of what and how to do curl and divergence, which are actually pretty simple to do. And then we're going to talk about the algebraic and the geometric interpretations of both of them. So really when we define them, we're going to define them algebraically. And then at the very end, we're going to talk about what they actually mean. So the first thing is, again, let's take a look. The curl of a vector field is defined to be del, the upside down triangle, cross F, which is our vector field. So this represents our vector field. And as you can tell, in this case, it's a three-dimensional vector field. Kind of has to be in order to do the curl, because in order to do a cross product, it must be three-dimensional. And then del, of course, hopefully you remember, is the gradient of f. So it's the partial with respect to x, the partial with respect to y, the partial with respect to z. So taking a look at this real quick, you should remember that we use the symbol for the gradient of the upside down triangle, which is del f, which is f sub x, f sub y, f sub z. That's the gradient. So the curl is defined to be del cross f. So you put across the top your I, J, K and your determinant. And then you've got the partial of x, the partial of y, the partial of z. That makes up the first vector. And then p, q, and r makes up the second vector. You don't have to write the p of x, y, z, the q of x, y, z, and everything. When you write the actual functions in there, you'll see that you're going to have x, y's, and z's. And then when you cross them. So again, remember that when you cross these things, if you do the I part, you're going to eliminate the I row and the I column, and then you're going to do the 2 by 2 determinant, which is left over, which is the partial of r with respect to y. So it's this part right here. Partial of r with respect to y minus the partial of q with respect to z. And that's going to get you the first component with I. And then remember that you change the sign of the second one, so it's now subtracting. Let me go ahead and erase what we have here. Let's try something different. Nope, that is not what I meant to try. Let's try this. Alright, that's pretty cool. The second component is the subtraction, or the minus. You're going to eliminate the j row and the j column. It's the partial with respect to partial of r with respect to x, which you see here. That's this part. And then the partial of p with respect to z, which is that one. And then the last one, I'm not going to circle that one, but it is kind of like this feature. It is the same thing, but now you do it with k. So let's go ahead and take a look at a couple examples. Okay, example 1 says, find A, the curl, and B, the divergence of the vector field. We haven't talked about divergence yet, so we will come back to that one at a later point in time. For now, we're just going to find the curl of this vector field. Again, this is very simple to do, as long as you remember your cross products. So the curl of f, oops, guess it would help to actually have a pen that writes. The curl of f is the determinant I, j, k, then it's partial with respect to x, partial with respect to y, partial with respect to z, and then we write the x, y, and z components of our vector field. Well, if you look up here, the x component is just the coefficient of I, which is 1. The y component is this one right here, which is x plus yz. And then the z component is xy minus root z. And then we're going to go ahead and take the determinant of that. So the first component, eliminate the I row and column. We have the partial of y times this one. So the partial of y of this one right here is just going to be x. So you're going to perform the operator, the partial of y, on its diagonal component. So that's just going to be x. And then this one is going to be the partial of z. So perform the partial operator on the component that it matches up with, and you're just going to get minus, was that y? Yeah. Okay, so hopefully that makes sense. I'm not going to keep circling these because it's going to get to be messy. But now you'll do the j part. And remember, the j is going to be the opposite sign. So we're going to put a negative in there, put a parentheses here because I know I'm going to have to subtract some things. So then you're going to do, you know what, I am going to go ahead and circle these. Let's see how this, yeah, let's do red. Partial of x on that one right there, that's just going to be y. And this is going to be the partial with respect to z. That's going to be 0. Okay? And then the last one, yeah, there's really no way I can do that last one here without totally messing all this up. So going to eliminate the I, J, K and the K column. So we're going to get the partial with respect to x. Let's see, of this piece right here, that's just going to be 1. And the partial with respect to y of this piece right here, and that's going to be 0. So our curl is x minus y, negative y, 1. That is the curl of f with respect to this function. Again, we will come back and we will do the divergence later. All right, so let's look at a theorem here. Again, doing the curl wasn't very difficult, but there's a theorem that says if I take the curl of the del f of the partials, then I should get the 0 vector. So let's actually go ahead and show that that's right. Now remember that del f is defined to be the partial of x, partial of y, partial of z. That's your gradient. So if I was to take the curl of the gradient, that's what it's telling me to do. Take the curl of the gradient. Well, let's set it up, and hopefully you should see why this works pretty quickly. I, j, k. So this is going to be partial of x, partial of y, partial of z. Remember, those are operators. And then I'm going to have the partial of x, partial of y, partial of z. So if I was to do the first component, eliminating the I row and I column, I get the partial of partial of z with respect to y, which is going to be written as, first we did the partial of y, then z, minus, then the second part would be the dz part of fy, so that's really going to be, we did the partial with respect to z, then y. Well, if you remember, before we get to the rest of these, by Clairaut's theorem, the two partials are the same. fyz equals fzy. Well, if that's the case, when we subtract those things, we're going to get 0. So the same thing is going to hold true for each one of these pieces. It's going to be exactly the same idea. You're going to get the second partial derivatives on each one of these. So what we're going to get ultimately out of this is 0, 0, 0. And you can go ahead and check the other two just to make sure that that makes sense. So the curl of del f, or the curl of the partials, is going to end up giving you 0, 0, 0. All right, let's take a look at this statement. It says that the curl of f, it says if the curl of f equals 0, then that means f equals del f, meaning that f is conservative. So that's really cool, actually, in the fact that it's going to tell us here, if the curl of the vector field is 0, then that means that f had to equal the gradient, meaning that f is conservative. So if we take the curl of a vector field and that equals 0, then now we know it's conservative. Remember, we said we didn't have a way to figure out this conservation earlier. Now we do. All this says is this works the other way too. So what we used to have was some vector field would equal some PQ in 2 dimensions. And remember, the idea there was to figure out if it was conservative if dp dy equals dq dx, then that means conservative. And that's what we had in 2 dimensions. Well, now we're just extending this idea, because remember that this could also be PQ0. You could extend that to 3 dimensions there by doing PQ0. So, yeah, I could do this without that. Curl of F is some I, J, K sorry about that, ddx, ddy, dz, and then you're going to have some kind of p of xy, q of xy, and then 0. So if you were to set this up, in the first one, you're going to eliminate the I row and column. You're going to get some kind of a derivative of y of 0. That's 0. Minus. Then you're going to have the derivative with respect to z of some q of xy. Well, there's no z, so that's also 0. Then if you do it with respect to the j part, once again, you're going to get the derivative of 0 with respect to x. That's 0. And then the the ddz of pxy, once again, there's no z in there, so that's also 0. Change the sign, still 0. And then it's the last part that if we do the k part, that's actually going to give us something. What it's going to give us is the derivative, or the partial derivative with respect to x of q of xy, which is just dq dx. dq dx. Minus, then if you eliminate the k row and column, and then you do minus the derivative with respect to y of p of xy, well, that's just dp dy. And remember, the idea was that if dq dx equals dp dy, then you have a conservative function. Well, if dq dx equals dp dy, dq dx equals dp dy, then the subtraction of those two things equals 0, and you end up with the curl of f equaling 0, 0, 0. So again, all of that was really just to show you that this works both ways. It works for both meanings.